pattern of resistance. And this was called later, it was called already before tunneling anisotropic magnetoresistance, but this is the first time it was observed in this metallic system. And then, I will tell you how we explain this. And then we propose this to experimentalists that while look at the vertical transport, one can also look at the lateral transport, and this is what I did more recently, and this is called crystallographic anisotropic magnetoresistance. So now we have gallium arsenide and iron. This is a bilayer system. Gallium arsenide is non-conductive, so the transport is only through iron, and it's only a few monolayers of iron. So the spin-orbit coupling from gallium arsenide gets picked up by iron by proximity effect. And I will show you results of this experiment. It's really fascinating. So based on this experience with spin-orbit coupling, which causes this transfer phenomena, we also propose what we call MAAR, magnetoanisotropic Andreev reflection, in which you take a ferromagnet, then let's say gallium arsenide or indium arsenide and superconductor, and rotate the magnetization of the ferromagnet, and you should see actually a huge effect due to the Andreev reflection and the spin-orbit effects at the interfaces here, more like 60% instead of, let's say, 1%, which is in here. So there are already experiments underway. And this is another effect that we propose as a tunneling anisotropic Hall effect, that because of the interfacial spin-orbit coupling here between ferromagnet and normal metal, if you have a tunneling current, there you should have a sort of a transverse current flowing in this junction. Okay, so this is the experimental example that I promised to show of this crystalline anisotropic magnetoresistance. So you take a few monolayers of iron on gallium arsenide, growing in 0,0,1 direction. In the 0,0,1 direction, if you cut the surface of, let's say, gallium arsenide, zinc-blende, or indium arsenide, you will see a picture like this. And if you would look closer, you would see that this yellow atom is on top of this plane, and this is also on the top, but this one is below. So this direction and this direction are not equivalent. So the symmetry is not C4V, rotation by 90 degrees, but C2V symmetry. And if you put iron on top of such a gallium arsenide, so iron has a four-fold symmetry, because of this interface, iron picks up this two-fold anisotropy. And this is a signature, okay, we have the word signature, is a signature of interfacial spin-orbit field, and you see it here in the resistance map, so it's a polar map of the resistance versus the orientation of magnetization in iron. And you see a nice C2V symmetry. So this is the 110 orientation, 1 minus 10, and this is 110. And there is a different resistance because of this interfacial effect. And this is a unique signature of the proximity-induced spin-orbit coupling in iron. Now, this was with 4 layers of iron, really just 4 layers, yes? You had a question? Oh, you don't understand? So, okay, current flows through iron laterally, and iron sits on gallium arsenide. And we change the magnetization of iron in the plane of iron. If iron would be four-fold symmetric, then this picture would be four-fold symmetric. If it's two-fold symmetric because of the interface, this is why it's two-fold symmetric. Then you change the number of monolayers of iron from 4 to 6. If you read horizontally, this is 6 layers. The symmetry is still the C2V, but there is it looks more like four-fold now. And then when you go to 8 layers of iron, the symmetry is four-fold, but the principal axes of the symmetry are rotated, because these are the principal axis of the bulk iron. So with 8 monolayers of iron, we could claim, based on this experiment, that the proximity spin orbit is gone. Essentially, you have a bulk iron. And I think this is a really beautiful experiment for the first time showing this transition from interface property to bulk property. And it's very important, I think, in this, the physics that you guys discuss. Now, how do spin orbit fields look like? On a simple model level, you all know how the Rashba field looks like, so Carlos showed it very nicely. Maybe some of you also know some Dresselhaus field, a little bit more complicated. But I will show you that it's, in reality, things are even more complicated than that. So this is something that we sort of know. It's a standard knowledge, and people who like to work with models, that they use it. So if you have a zinc-blende quantum wells, let's say gallium arsenide, indium arsenide, if we have a structure inversion asymmetry, then linear in momentum spin orbit terms is the Rashba term, and the spin orbit field looks like this. So it's the famous Rashba picture. Now, Dresselhaus field can have various patterns. If you grow your quantum well in a 0-0-1 direction, there is this C2V symmetry that I just discussed. And in addition to this, you get the Dresselhaus field, which has this structure. And this is what most people use for the Dresselhaus field. Now, if you grow your semiconductor in 1-1-1 direction, then what we would call the Dresselhaus field looks exactly like the Rashba field. It's completely different from 0-0-1. It looks like this. And if we grow the Dresselhaus field, we grow the semiconductors along 1-1-0 direction, then the spin orbit field is out of plane. So the spin is polarized out of the plane of the semiconductor. And this is all discussed in the many experiments. In also, let's say Sergei Garnichev in Regensburg is an expert on this. So the Dresselhaus field that we know is just one particular example, and people just use this maybe and this, but it's much richer physics. Say again? A beta would be this. This is alpha. It depends on the heterostructure, on the material conditions. You cannot just say it. No? Okay, this were just linear terms. Suppose you go to cubic terms, so it has to be over linear, cubic to preserve time-reverse asymmetry. So there is a cubic Rashba. Probably nobody heard of a cubic Rashba, but there is. It has to be, right? So if you go away, there has to be cubic Rashba. There is a cubic Dresselhaus. Of course, people know cubic Dresselhaus. So the cubic Rashba for this particular crystal would have a C4V symmetry. The cubic Dresselhaus has a D2D symmetry. But they together provide C2V symmetry. So Rashba and Dresselhaus is sort of a misnomer because they come together as C2V spin orbit fields. Every group symmetry has its own spin orbit field. It's just by accident that we call it one Rashba, one Dresselhaus. One should also be aware of that. And then if we have those two, then spin orbit coupling can have very different patterns. And that's just cubic. Then you can go to the fifth order, whatever. 7th, 11th, that doesn't make sense, right? So at some point one has to stop. So how do these fields actually look like in a material system? So we first modeled this tunneling anisotropic effects by phenomenological models, Rashba, Dresselhaus, linear, and so on. And things usually work because these are robust descriptions. Like when you use Rashba for Majorana, it's a robust description. But it's realistic at certain level. For certain phenomena, it's not clear. For some phenomena, it works. For others, it need not work. Usually, these descriptions preserve symmetry, so you get some description, and then you fit to the experiment, and you get some fitting parameters. That's all what you can get. So, for example, this is a phenomenological theory based on linear Rashba-Dresselhaus, and we fit the experiment very nicely. But then we started to look for the actual spin orbit fields for a particular slab, like this one. This would be iron. This is gallium arsenide. how would the spin orbit fields look in such a slab? So if you look at the symmetries of this slab, if you look at the top, so these are iron atoms, this is gallium arsenide, these are the mirror planes, sigma xz, sigma yz. So this is the C2V symmetry, has only 4 group elements. And if we have this symmetry, the only linear spin orbit coupling in momentum that we can have is this combination of kx sigma y, ky sigma x, in which x and y are the principal symmetry directions. So 1, 1, 0, 1, minus 1, 0. And this is the C2V spin orbit Hamiltonian, which you can rewrite as a sum of the Dresselhaus and Bichkov-Rashba. So this Hamiltonian is equivalent to this. So historically, we call it Dresselhaus or Bichkov-Rashba or Vasko-Rashba, whatever. There are a couple of Russian names associated with that. So people just pick up Rashba because the common denominator in those. And then, but then you don't have to stop here. You can expand it to higher orders in momenta, and you get some general descriptions for C2V spin orbit fields. Okay, so this is a phenomenological model that we have, and we like this model. It's simple. And then we look at the electronic structure. So this is the electronic structure of a particular slab, 3 monolayers of iron, of gallium arsenide, and you get some spaghetti. And then, where is your Rashba, where is your Dresselhaus, what is the spin orbit field? It's not so simple. To get the Rashba and Dresselhaus, linear or cubic, you look at the gamma point, because these are the expansions around the gamma point, nothing more. Small regions around the gamma point. If you look at spin orbit coupling in a metal, that's absolutely, an incorrect way of doing things. You have to look at the general momentum, let's say the Fermi momentum, and figure out what is the spin orbit coupling, spin orbit field there. But this is a tough job. It took us a while to figure out. But we figured it out for this particular system or for ferromagnetic semiconductors. And we could extract from ab initio band structure, but playing with different magnetization orientations, spin orbit fields at a particular momentum. Not directly at gamma, but let's say somewhere around. So for example, this would be spin orbit fields very close to the gamma point, and it looks like a nice Dresselhaus and Rashba. This would be farther away from, let's say, 12% of the Brillouin zone. It looks different. In addition, the spin orbit fields do depend on the orientation of the magnetization. So if you change the magnetization of iron, let's say from 1, 1, 0 direction to 1, minus 1, 0 to 1, 1, 0, spin orbit fields can even flip these Rashba fields. So one should be careful also. Oh, this can actually give an additional control of spin orbit field. So this is how we sell it to PRL. A control of, so it's not a nuisance, but it's a control. It could be. So you can control your Majorana fermions by changing magnetization in European sulfide and changing the spin orbit coupling. Could work. So let's say very close to the gamma point, this is the usual C2V spin orbit field that you have a Rashba Dresselhaus. So this is the momentum space. And when you change the magnetization from this to this, spin orbit field change. We can fit then this extracted spin orbit fields, so this Rashba and Dresselhaus linear in momentum prescription very close to the gamma point, and we obtain the values for Rashba and Dresselhaus. If we go away from the gamma point, then we have something that we call spin orbit field butterflies. These are really beautiful sort of C2V patterns of spin orbit fields. You would not describe them with a simple model, certainly not linear in momentum. One simply should be aware that if I have even a thin layer of a metal, then spin orbit fields are more complicated in reality than Rashba and Dresselhaus. So for let's say for transport, for understanding the basic qualitative effects, one could certainly use Rashba and Dresselhaus fields, but at the end, you will get, I think, the right phenomenology out of it, but not really quantitative description. Okay, so this is how we got to the spin orbit fields, and we already did a calculation, as this is an example, for iron and gallium arsenide, because it was important for this particular experiments. Then we got interested in zinc-blende and wurtzite semiconductors because of Majorana physics, and also because some colleague of mine also grows nice nanowires I will show you. And it was very important to understand, let's say, the G factor of wurtzite materials because it's not really much known. So all these ab initio calculations were done by Martin Kmitra in my group. So now it's an introduction to zinc-blende and wurtzite. So as Peter showed, these nanowires can grow in zinc-blende and wurtzite in a controlled way. And Carlos also has some nice ideas about those things, what to do with them. So let's say if I take indium arsenide, it can grow in the zinc-blende structure, so cation, anion, and so on, or in a wurtzite system like this. But they look different, but if you look from the 1-1-1 direction, they are sort of very similar, nice hexagonal system. So it's like a hexagonal close packing. This is ABC, this is AB, AB. They look sort of similar, but the band structure of wurtzite and zinc-blende are different. So the zinc-blende band structure has the usual conduction band in the double group representation gamma 6C. This is where you have this Rashba Dresselhaus effects. And then there are also heavy and light hole bands, gamma 8V and gamma 7V for the valence band, and they are split by spin orbit coupling. If you go to the wurtzite structure, then you also have heavy and light holes, but then there is a crystal splitting between heavy holes and something which is called crystal holes, CH. So it's a little bit more structure in this wurtzite. But the band structure actually is not so well known for these materials. Mainly it's induced from nanowires experiments, but nanowires, because of the confinement, can, for example, give larger band gaps and so on. So this is schematics for zinc-blende and wurtzite along different directions. So this is the Brillouin zone of a zinc-blende semiconductor. This is the Brillouin zone of a wurtzite semiconductor. It's a nice hexagon. And these lines show directions, for example, from the gamma point to the X point. So gamma point is here, X point is directly here. And you see if you go along this line, which is called the delta, there is no spin splitting, for example, along this line. If you go along 1, 1, 0, so if you would grow your nanowire along this line, you would not see much of a spin splitting. If you go along 1, 1, 0, so it's a sigma line, this one, then you see a splitting. And this would be the Dresselhaus splitting that I talked about. Again, when you go along 1, 1, 1 nanowire, no splitting. So for wurtzite, you always get a splitting unless you go directly along the principal axis of the hexagon, which is 0, 0, 0, 1. So hexagon has these 4 symmetries because it has three planes cutting your axis. So in wurtzite, generally, you would have some kind of even linear splitting in the conduction band. This splitting here is cubic. So zinc-blende is well understood. It's Jean Dresselhaus had this paper in 1955. Essentially, he had hidden somewhere this formula that the spin orbit coupling is described as the spin orbit field, which we call the Dresselhaus field, times sigma, and this coupling has this general form. Kx, ky, kz are momenta. So for example, if you go along 0, 0, 1, so it's only kz is non-zero, but all other kx, ky are 0, you get 0, right? If you go along 1, 1, 1, all of them are the same. This is 0, this is 0, this is 0, you get 0. So this formula predicts that along 0, 0, 1, along 1, 1, 1, you should have no intrinsic sort of splitting due to spin-orbit coupling. There are no spin-orbit fields. And if you want a sizable splitting, then you have to break, you have to induce structure inversion asymmetry with the Rashba effect. Yes? Mm-hmm. It will be 0, yeah. If it will preserve the symmetry. If it doesn't, then exactly. Then it will be the Rashba effect, and then it will not be 0. If you put aluminum on a side and so on. This is what yeah, absolutely. I know what? The berry phase? Yeah, what is the berry phase? This is not a topological insulator. No, it's just a normal semiconductor. Just no topology here, sorry. But okay, so these are the spin textures. So you could calculate the binding numbers, for example. That's the most topological thing you can get here, probably. So this would be the spin texture for light holes, spin texture for heavy holes looks quite nice. For the conduction electrodes, it's just regular spin texture just coming from this. This is an actual calculation of a zinc-blende indium antimonide. Along gamma X, you see no splitting. If you gamma K, you see nice splitting. It's a standard calculation. We have done this calculation of zinc-blende for gallium arsenide, gallium antimonide, indium arsenide, indium antimonide in this paper that came last year. And I think this is the most comprehensive DFT analysis up to date. So we compared for zinc-blende with GW, which is the state of the art, although also in the GW one has to do some manipulations. And this Dresselhaus parameter gamma, we calculated, let's say, for gallium arsenide to be 9, roughly. In the literature, actually, this is not well known so much. The values range from 9 to 28. Lately going towards 9, like GW, because in the literature, people take the simple model, make a complicated experiment on a complicated system, and fit the simple model. So this value of gamma in experiments is to be considered as a fitting parameter, not a real description of a band. Let's say you have 5 subbands and so on. Your numbers will be different. So this was encouraging, and then we went to Woodside, because in Woodside, as I said, no calculations like that, nothing much is known. So this has to be taken as a prediction. But even in Woodside, the spin splitting of the bands are sort of known. There is an analytical description. It originates by Rashba, but it's different from the Rashba effect that you apply electric field gate and so on. So Rashba considered really Woodside structures in 1960, and he predicted that in the conduction band, there is a linear in momentum spin splitting. In zinc-blende, it's cubic. Dresselhaus is cubic. But Rashba is already linear. You see it here for the gamma 7 and gamma 8. So gamma 7 is the conduction band. You have alpha times linear in momentum. So in the Woodside, you have linear splitting in the momentum. That's quite miraculous. And then you have also cubic terms. So based on this description, you just look at the direction, and you can figure out, what is the splitting. So for example, the spin pattern in gamma 7, gamma 8 looks like this. And gamma 8 is the heavy hole band. It looks like this. This is our calculation. And again, we tabulated it in our paper. All these properties are here. We fit these structures. So if you grow your nanowires, you can have a look here and figure out how much spin orbit you can get as a benchmark from this Dresselhaus effects. We then also calculated things like G factors, because they are very unknown for Woodside materials. For example, we calculated for but these are bulk. These are bulk for indium phosphide and indium arsenide. And actually, these results are in perfect agreement with recent experiments in the group in Rome by Antonio Polimeni. So, they really measure these G factors by doing optics on these nanowires. So I think these values are quite reasonable. They have quite large diameter nanowires, and they look at optics in the presence of magnetic field, look at the splittings of the levels and so on. So we started with the DFT, and then the next stage is to look at the larger structures, in particular nanowires. So I have a very nice collaboration with a group in University of Sao Paulo in Sao Carlos. I'm actually going there next week. I got this research award, Science Without Borders, which gives me this nice opportunity to collaborate, and the calculations are done by Tiago de Campos in the group of Guilherme Sipahi, and Paulo, who will be, actually he is a Humboldt Fellow now in Regensburg with me, did the K.P theory. But we got also interested in this because in Regensburg we have a very nice semiconductor growth group by Dominique Boujard. And this is an example. So Dominique grows this nanowires, wurtzite nanowires of gallium arsenide. And then he grows all this forest of nanowires, and he then kills most nanowires except one. And then he shines line on just one nanowire and does the Hanle effect in the presence of a magnetic field. So by optically shining circularly polarized light, he excites spins in this nanowire, applies a magnetic field, and looks at the precision of the spin in the nanowire, which gives the G factor of the nanowire and the spin orbit field. And this particular experiment was interpreted by us as there is a spin orbit field, like a bulk field of the nanowire, and the spin orbit field at the interface that gave interpretation to the experiment. So when we have this DFT bulk band structure, we do K.P modeling, or K.P when a magnetic field. You see the modeling here, it perfectly fits the DFT band structure. So this K.P model for wurtzite is in this paper already published. And then we'll do large structures in Sao Paulo. So we take a hexagonal nanowire, but we have also square and circles for zinc-blende and wurtzite, and look at the band structure. So, for example, this would be a nanowire of 50 nanometer, indium antimonide, zinc-blende, hexagonal structure along 001. So this would be the lowest subband, no spin splitting according to the formula that I gave. And then you apply an electric field transverse to the nanowire, like here. This is our way of introducing Rashba. And then you see this nice splitting. And then you fit this splitting to the Rashba and see what is the Rashba energy, and also with other growth directions. And then this is the Rashba energy for the fields in the nanowire of the order of, let's say, 10 to minus 4 volt per nanometer, which would be something like 0.2, 0.3 volts across the nanowire of 100 nanometers, roughly, because of the dielectric constant inside the nanowire. And the Rashba energy here is in 0.01 millieV. Not so large. So let's say 4, 0.04. I know Leo Kuvenhaven said, I need 1 millieV. Well, most we got from different directions, something like 0.4 millieV in these nanowires. This would be wurtzite, indium arsenide, again hexagonal, sort of similar structure. You get many bands and so on. You do the analysis, and in this particular direction, it should be actually 0001. So again, the hexagon, you get even less, because this is the value multiplied by 100. Along other directions, it's more, but we haven't reached the 1 milli electron volt in these nanowires. Okay. I have some few minutes left, so count it as the discussion time. Okay, I'm almost done. Okay, so now we want to go from bulk to slabs just from ab initio. This was K.P, okay, what ab initio gives. And I will show you just one particular example. You take a slab of a wurtzite indium arsenide and do everything ab initio along a particular orientation, 1, 0, 1, 0. Yeah? And you have an ideal structure of a slab. So this is a cross-section of the slab. And then a relaxed structure. So you relax the surface atoms to find a minimum energy. And then you look at the Rashba energy. So you take this lowest band, which comes from arsenate, look at the Rashba splitting, and ideal would be 0.1 milli-electron volt, and relaxed 0.08. Huge difference. So this Rashba is so sensitive to whatever you do in the sample. So I know, if a wind blows over your sample, you will get a different Rashba, you know, sort of like a butterfly effect, but it's really very sensitive. It's astonishing. So at the end, this DFT maybe will give experimentally some benchmark, but at the end, you just have to figure out Rashba for yourself, what it would be. We are still working on it. Okay, the next complexity level is nanowires with electrons. So we discussed nanowires with aluminum, right? Okay, we have this calculation, aluminum on the wurtzite indium arsenide. Okay, now just look at this mess, right? So you get a lot of spaghettis. It's a strong hybridization. Now, what is Rashba here? Everything is strongly hybridized. So aluminum is a superconducting. Imagine it as a superconductor. All the bands will be just messed up. So we are working on it. We had similar complexity with iron gallium arsenide, but we simply have to figure out how to abstract some simple description that people like to do and give some reasonable values, sort of understanding. I was recently reading an article in the New Yorker about a philosopher. He always say that we sort of understand things. So this sort of understanding. And I just prepared this slide because of Peter's talk, and we had discussions about this. Proximity exchange. So for this Majorana fermions, you need large G factors because your Zeeman energy should be greater than the proximity-induced superconducting gap to be in the topological region. So that's why you need large G factors. The alternative approach is to have a exchange proximity. We have plenty of experience with that in 2D materials. So we put, for example, graphene on different ferromagnets. This is an example of graphene on chromium silicon ditelluride. It's a ferromagnetic insulator. And this is a calculation. You see nicely graphene band structure. And if you zoom in, you see splitting of a few milli-electron volts, which I think would be quite fine for Majoranas. But this is just one layer of a material, just a monolayer of graphene. Now, for indium arsenide, you have, I don't know, 100 layers. So let's look at so Martin just sent me this calculation, proximity exchange iron on gallium arsenide. So as I'm skeptical, one should try. So this is a magnetic moment in this particular material across going from iron. So we have 9 monolayers of iron. You see stable magnetic moment. And then what is the proximity magnetic moment in gallium arsenide? It just drops to 0. In arsenide, in gallium. Now, the question is, what is actually 0? I emailed Martin because for you maybe 10 to minus 3 would be already enough. I have to figure out what it is, but you have really 100 layers here. So I don't know what do you expect the proximity. If you want to have a large magnetization in the semiconductor, you have to inject this spin. But by proximity, as I said, I'm skeptical, but one should always try. Experimental is more powerful than theories at the end. So, okay. Say again? Oh, yeah, exactly. No, okay, so this is a calculation for a slab like this with 9 monolayers of iron looking at the total magnetic moment at a given layer. Maybe I don't hear you properly. Yes? Yes, no, I understand your point. This is the total magnetic moment at the monolayer. We haven't yet looked at the actual splitting of the bands, which, like for graphene. This is like a 5-year-old calculation that I just got before this talk, just to show something. But we will have more information. But based on our experience with graphene, I'm skeptical. And this is iron. This is a metal. Yeah.
I would be also skeptical to couple like indium arsenide nanowire with aluminum, because the other is a metal. Indium arsenide is semiconductor, and there is large mismatch in the Fermi momenta. So I think the physics of interfaces is more complicated.
Oh, okay, it depends what you want as a proximity. Superconducting proximity is different.
No, but it's the same effect. You're trying to induce exchange splitting in gallium arsenide.
Correct.
By virtual tunneling of electrons into the iron, right?
Correct.
So the same happens in superconducting proximity effect. You're trying to induce superconducting pairing by virtual tunneling of electrons from indium arsenide into superconducting.
Correct. So superconducting proximity is up to, let's say, 100 nanometers, 10 to 100, right? Yeah. Can you imagine that you have an induced spin just in equilibrium, iron and indium arsenide, and you go to 200 nanometers? Yes?
Well, first of all, there are materials.
You can do the Kerr effect, and people do that routinely because we do spin injection. Only in spin injection, which is a kinetic effect, non-equilibrium, you have this injection going to maybe 200 nanometers. And it just decays very quickly.
Sure,
it's a very different effect.
No, but let's imagine the thickness of
I'm essentially done, sorry, because I have to. This is a discussion already. So the superconducting proximity effect is, let's say, Andreev reflection, right? Sort of the Cooper pairs are coming there. There is no really attractive force in indium arsenide. It's sort of like Cooper pairs are flowing there, and until something happens. This effect really is from the interface hybridizing the orbitals from iron to non-magnetic materials. No? Mm-hmm. 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 Okay. So there is one. There is one over there.
It's a different question. So,
okay.
Out of curiosity, so and it's a question about experiments, if you know.
Uh-huh.
So in indium arsenide, if it's a thin layer, okay,